SQL, you'll also hear SQL, is structured query language. So it's a language that lets you access and manipulate data in a database. At a really high level, that's what it is. It's an ANSI standard, so it's American National Standards Institute standard. So you can use SQL all around the world on different types of SQL databases, but it's important to know that there are different dialects. So while you might be able to use the core concepts in SQL on something like Oracle or Microsoft SQL, they do use slight variations, and you might even hear them called slightly different things. So Microsoft SQL Server uses a dialect called T-SQL, has its pros and cons just as much as MySQL does. So what can you do with SQL? With SQL, you can execute queries against a database. So what does that mean? It means you can retrieve or bring back data. You can insert, so add new data. You can update, which is basically change the value of data, or you can delete data. But you can also do things related to the database itself. You can create new tables. You can create all kinds of different kind of structural concepts in the database. And with SQL, you can create reusable blocks of code. So you can make things like functions or stored procedures. We're not going to cover those in this course, but it's important to understand that with SQL, you can write reusable code. So what's really important to understand when you're using SQL is how are databases typically laid out? What are the key concepts that you need to understand so that you can write queries effectively that really solve the questions that you want to know? So the first portion to understand is a database. So it's basically a container that holds tables and other SQL structures related to those tables. You might think about it like a file in a filing cabinet. So you could have multiple databases, but within each file, you probably have related items. And in that database, you would have tables. So let's take the filing cabinet example. In the file, you have different pieces of paper. Each of them have different information. Maybe one has orders, one has addresses. On a piece of paper, it might be laid out like a spreadsheet with rows and columns where that intersection is called a cell. And that's important to understand too. The data itself is organized into columns and rows. Different databases store these in different manners, but kind of that tabular the concept is important to understand. If you're familiar with Excel, kind of already familiar with the format, that's kind of how you can think about the way the data is stored at a really high level. What's something that's really unique and important to understand about SQL is data types. So if you're familiar with Excel, you might not have come across this problem, but it's super important in SQL and SQL databases to understand that data types can be different types, and those types mean different things. So let's look at the first two. So you might not be familiar with Boolean. You're probably familiar with integer, but a Boolean is basically a true or a false, a yes or a no, an on or an off. And that's really important to understand, but it can also be completely empty. So that empty concept is called a null. Almost all of these data types can be a null, and that basically means unknown, unknown. So if you had a true or false, let's say you have a column and you call it is final. And if that record is the last one, you want is final to be true. And if it's not the last one, you want it to be false. If for some reason you can't figure out if it's the last one or not, you might leave that as null. And that's really important because if you have this on-off type situation, you could use an integer and store a 1 or a 0. It would totally work. But what happens when someone enters a 6? What does that 6 mean? And more importantly, you're starting to take up space that you don't really need in the database. So an integer would be a number. You can see the different dialects that kind of have different names: int, number, integer. A float is also a number, but it has a greater range of values. So while an integer might be 7, a float could be 7.249236. If you need just the whole numbers, use integer. If you need the kind of the decimals, you might want to use float. It's important to understand how these things interact when you do rounding or addition or subtraction. We're not really going to cover that in this course. It is important to understand that they behave differently. Some databases have this concept called currency. You can see Access SQL Server do, MySQL doesn't. Also important to understand, we're not going to dig into that either. What we are going to start to dig into is this concept of a string. You can kind of think of a string as text, but it could really be anything. You can store numbers in a string column. They're going to behave differently than in an integer, but you can store numbers in there. You can store words. You can store different languages of characters. And typically you have two concepts, fixed or variable. So let's take a really specific example. If you have a column called middle initial, you might want to put that as car1, so character 1, which basically means that column will only have one character and can never have more. It could have less, you could have it completely null. Um, but for varchar, you might not know how long things are going to be. Let's say you don't quite know how long um, a first name is going to be. If you don't want to define a number, you could say car 150. That might work. But if you want to do varchar, you could allow the database to basically size it as it goes. And this might help you with optimization for queries and for your database. From a query concept, it's just important to know that these strings, car and varchar, can have all kinds of stuff. They can also have numbers, but they will behave differently. So that's kind of an important kind of nuance to recognize. Binary object can store all kinds of things. Images are a common one. It can store, raw binary data. Not really important for this course, but important to understand that there is this concept of a binary object data type. Let's dig in to the words relational data and normalization. We're going to talk about both of these. They're important concepts to understand. If you're working with the data warehouse, you might not really encounter them, but you probably will hear people talking about them, especially if you're working with the transactional system. So that might be something that's like taking orders from a website, where it's really important that every order gets logged in an absolutely correct manner as fast as possible, where in a data warehouse, that might not be what we're optimizing for. So what makes a database relational? So relational is exactly what it sounds like. Some data relates to some other data. And relational typically goes hand in hand with normalization. So in this example, we have some data that's not really normalized. It's probably what you would call denormalized. And it has information on artists and their albums. So you can see Britney Spears has 3 albums. LFO has 1 album. This seems to work fine, but what happens when Britney comes out with the 4th album and the Backstreet Boys come out with the 16th album? Then you can see how this can start to get unwieldy. So with relational data, we can compare information because of the arrangement of data in the columns. We can build new tables out of required information from existing tables. And we can use relationships of similar data to basically speed up and make our database more flexible. So all of that is kind of abstract. So let's look at a little bit more about normalized data, and then we're going to look at an example. So we're going to take this denormalized data and set it up into a relational normalized process. So before we do that, you probably need to know what is normalized data. It's no repeating groups of data. So that would be, say if you have an address book, you might not want to have the state over and over and over and over and over again, or the metropolitan statistical area. Instead, you have a key that takes you to that state table. All non-key attributes are dependent on a primary key. So let's kind of dig into that. A primary key, that's basically a key that identifies the record as a discrete item. So for people, let's think about your social security number. It's actually not a very good primary key, but let's think about that. Your social security number identifies you as a person. So this is basically saying all the non-key attributes depend on that. So that might be your age, it might be your address, it might be your shoe size. All of that depends on your social security number. On the flip side, all non-key attributes are only dependent on the primary key. So in this past example, you might think, oh, everything is dependent on the primary key, the artist name, but it's not quite, because we're looking at albums and we're also dependent on the column name. So if we wanted to get all of the column or all of the albums, we'd have to get all of the column names and the artist name in order to figure that question out. And in a perfect world, we wouldn't want to do any calculation and store it in the table in a transactional database. For a data warehouse, that might be perfectly acceptable, even necessary. But it's important to understand kind of what we're talking about when we say normalization. So why does that matter? Really for 2 main points: eliminating redundant data and ensuring that dependencies make sense. So we're going to talk more about that second part, ensuring dependencies make sense, by taking this past example and setting it up in a more normalized fashion. This is the exact same data that we had in our prior example, but now we split it out into 2 tables. The first one is albums, and the second one is artists. And you can see each table has their own primary key. Album key is the primary key for albums, and artist key is the primary key for artists. And we can say for certain that if we're ever talking about album key, we're talking about, or album key 1, we're talking about Baby One More Time. And if we're ever talking about artist key 1, we're talking about Britney Spears. We don't need to look up any other information to identify that. And you might think to yourself, why don't we just put Britney Spears' name over here where it says artist one? And we could, probably isn't the best plan, because what happens when Britney changes her name to just Britney? Now we have to go through and update 1, 2, 3 columns, or 3 records, which doesn't seem bad, but this might ripple into hundreds of thousands of records. By having it set up in this manner, we would have to change 1, and everything is automatically linking back to Britney Spears. And we connected those, kind of in this example, we connected it through the primary key and the foreign key. We're going to talk more about those in a moment, but ultimately the primary key is the key that identifies the record that we're looking at. So artist key is a primary key for artist, and the foreign key is how we're linking other data back to that. So in this case, album key is the primary key for albums, and artist is the primary key, or is the foreign key that links it back to artists. You can see we can have multiple foreign keys, but we don't have multiple primary keys. And in addition to that, there are different types of relationships. There's one-to-one, which might be your social security and maybe your full name. Let's say in an imaginary world, there can only be one person with your name. You would say your social security number identifies you as a person. There can be one-to-many, and that might be something like if we are doing addresses, we could have one address with multiple people at it. And there can be many-to-many, and that might be if you're looking at people across all time, many people could have the same address, and that address can have multiple people that have lived at it. If we're talking about different types of families. It's important to understand that the primary key is what identifies the row in the table, is typically identified with the letters PK, and the foreign key is kind of how we connect back to that primary key using kind of this relationship concept, and it is typically denoted with the letters FK. About select and from. So these are some really key clauses in SQL that you would use to basically bring back a select amount of data. So we're basically going to write it in this order. We're going to do select any column names that we want. Remember, a column is the vertical portion of the table. From, and then indicate the table name that we want. We'll get to the where, the group by, the having, etc. later. So let's take a real life example from our handy dandy database here. This is the track table. So at the top, that large table is the track table. You can see we have 4 columns: track ID, album, track title, and track length. And what we want to do is just bring back the track title and the track length. So to do that, we use our keyword select. We list the 2 columns we want, which is track title, track length. They're separated by commas. And then we use the keyword from, and after from, we want to indicate the name of the table, and in this case, the name of the table is tracks. So you can see the top is the raw table, the bottom left is our query, and then the bottom right is the results that come back, which is basically just a slice of that table vertically, showing us the track title and the track length. Now, what we could also do is, let's say we don't like the name track length, and we want it to show as the word length in our report. We can use something called an alias. So top, exactly the same table. The bottom left is the query, almost the same as before, but a little bit different. You can see after track length, we have the keyword as, and then the new name, which would be the alias length. And what this will do is in our report that comes back, it will show the word length instead of track length, but it doesn't actually change the table itself. So the table will always remain the way it is at the top. But in our results, we'll have track title and the word length, where we show the length of the track. So that's a really easy way to use an alias. A lot of times the column names in the tables might not be super friendly. If you're doing reporting, you can do as and then change it to something that your stakeholders might appreciate more. So another thing we probably want to do is filter out our data, and that's where the where clause comes in. So we still need to use select, we still need to use from, but now we can add a new clause, and that clause is called where, and that basically lets us tell the query what to exclude or include in our results. So let's take a real life example of that. Same table, similar query. You can see in the bottom left, track title, track length from tracks where album equals 66. Now, that where is really important because that basically tells a SQL query, after the where, I'm going to have some sort of expression that will either evaluate to true or false. So where album equals 66, when that is true, it brings it back. If it's false, it does not. You can see in our results, we have Genie in a bottle, which is length 333. And if you look at the bottom row of the table at top, that album number is 66. Now, I want to point out something a little bit interesting. In our query, 66 is in quotes. So in an earlier section, we talked about different data types. In this case, if it's in quotes, we're treating it like a string or a varchar, depending on the way you want to think about it. We could have done it just 66. That would have worked totally fine too. I mainly wanted to put it as a string to let you know you can wrap quotes around something to make it a string. If you had a space, if you have numbers that you want to treat like a string, it's a totally possible way to do things. It might not be the best way, but it's important to understand that it is possible. So far, we've selected columns, we've chosen a table, we've filtered it down to a specific example. That alone should give you enough information to start writing some simple reports. But what if your reports come in sort of a funky order and you want to order them in a specific manner? So a really good example might be by like year, month, week, day. If we want to force that order, the data in our table probably isn't ordered the way we want, but we can use another clause called order by to determine the order of the results. Now, by default, this will go in ascending length. We can also write the keyword DESC after length, and that'll force it in descending. And all this does is it brings back the results of your query, and then as it outputs it to results, it will sort it in order by the column or columns that you've chosen. So in this example, we have order by length, and you can see automatically sorts it in order, and we have two ties. If we wanted to tell this query how to handle a tie, we could do order by length, comma, track title, and then basically what it would do is it'll order by length, and in cases where the length is the same, it'll then order it by track title alphabetically. So this is really important to know. It's really helpful with formatting. It can also be helpful with some logic-based queries if you're trying to get the first or last thing. But what you'll likely use this for is reporting, and order by can really make it a little bit easier on your stakeholders to understand the data that they're looking for. About aggregates, there's a bunch of things you can do to your data to reduce them down based on the aggregate functions that you choose. So some of the most common ones are what we'll talk about today. There are more, but let's just cover the core concepts so that you can get started and start using them in your everyday work. So really the core aggregates to know are count, sum, average, min, max, and last. So most of the aggregate functions, with the exception of count, work on a single column of numeric data. Now, last and count are a little bit interesting, but for sum, average, min, and max, typically you'd be using this on numeric data. Now, you could use it on non-numeric data. It's probably just not going to work the way that you like. And oftentimes when you're using an aggregate, you want to use an alias to name the result. So we talked about alias earlier on in this course. You can use as and then the name that you wish to alias in your select statement. You can do that on aggregate. So instead of saying count star, star is a great wildcard for all. Keep that in mind. You can do count star as total count, and then your column total count will have the count of all the things. So let's dig into some of these functions. Count. It basically brings back the number of rows. It doesn't really matter at the basic level what's inside of it. If it's null, if it's 1, if it's 0. When you're counting something, you're just saying, do these things exist? Now, later on, we'll talk about case statements, and you can start to get pretty complex with case statements and count and sums to do some more complex work. But for the purpose of this section, just think about counting as just basically that, counting. You can dig a little bit deeper if you use sum, which is basically like addition. It'll sum up the values in a single column. So you're not summing two columns together. Let's say you have something like duration. You're summing up all of the duration, and that will give you the total duration across all the records. Average behaves the same way, but instead of getting the total, it does the sum divided by the denominator, or basically how many records there are, to give you the average across all of the values in that column. Min and max, also pretty simple. Min will give you the lowest value, max will give you the highest. In numerics, min would typically be like a 0 or a minimum number. Max might be 10,000 or something. But it really doesn't matter what the range is. It'll just find the very lowest and the very highest. Now, last is a little bit interesting because typically you use last with an order by, and it will give you the last value in that selection or in that group. It might behave the same way as min or max if you sorted numerically, but it could behave a little bit differently if you sorted by a separate column. So we're not going to dig too much into last, but it is important to know that last and even first exist. So let's talk about aggregating our data. In this example, we are going to do a count, a sum, and an average, and we're going to group by length. So we're bringing in this group by concept. So top is our typical table that we've been working with, has the track ID, the album, the track title, and the length. And we're going to do a couple aggregates in the single query. So because we're looking at different columns or even the same column in different ways, we don't have to write multiple queries to solve this question. We can say, let's find the count of all records, the sum of the length, and the average length, all in a single query, and we want to group it by length. So our first portion of the query is count star. We briefly mentioned that the star is the wildcard for all. So count all as count, and that'll basically give us the number of records. And you can see in our results, count is number 3. We've aliased it as the word count to bring it back an easy to understand value. Sum will then take the total sum of all of the track lengths, so that's 225 plus 333 plus 333, and give us a total of 891. We've aliased that as sum. And average will basically give us the average track length, which is probably more helpful than the sum of the track length in this example. And we can see that the average track length is 297. And we have to use from to tell us what table it's from, and we use tracks. And we're going to group by length. In this example, that really doesn't make too much of a difference. But let's continue on, and we're going to dig into the grouping. So in this example, we have a min, a max, and a last. You can see that max and last happen to be the same, just given the order of the table. But min in this example gives us the lowest track length, and max gives us the highest track length. Last happens to give us the same, but it wouldn't have to. Basically, it's just saying in the current order of the table, which since we're not ordering it is not really guaranteed, the last value is 333. Now let's dig into group by a little bit more. So in this example, we want to get the count of the tracks and the track length. So ultimately what we want to see is for every track length, how many tracks have that same length? In this example, you can see track length of 225, we would expect a 1, and 333, we would expect 2 because we have 2 tracks with that length. And if you look at our results, we have exactly that. We have a track count, and we have the track length. Now the count star is basically counting all of the instances of that length, and the length is basically showing us the length of the track. And because we're grouping by length, we are basically reducing down those results to the unique values of length. So basically, if we want to figure out counts of a certain thing, groups of a certain thing, if we use the group by, it'll perform the same aggregations, but in a group over group type of manner. Now, let's talk about halving. Halving can be a little bit confusing. It takes place after the group by, but ultimately it's a way to filter your results after the grouping. Now, you can't use a where after the group by just because of the way that SQL executes, but you can use halving. So in that previous example, we saw we had one track of a length 225 and 2 tracks of length 333. If we were curious and we wanted to say how many tracks have, or how many records have a count of more than one of a given length. So how many times does this track length occur, and only show us the ones that occur more than once. Now we can look at this example and say 225 occurs only once, but 333 occurs more than once. So as we would expect, the results are a track count of 2, which is how many times that specific length occurs, and the length of 333. But now, instead of that previous example where we had 2 results coming back, we only have the results that meet our halving criteria. And you can see in our halving criteria, we have an aggregate, which is count star greater than 1. So you'll see this a lot of times. We could have said, show us all of the results where the average length is greater than 333, or the number of letters in track title. But typically what you'll see is after the group by, some sort of halving constraint that limits your output results based on another aggregation, either count or sum or average. So if we were looking at something like employee departments, maybe having a total salary over $1 million, we would first group all of the salaries by department and then having a sum of salaries greater than $1 million. It's a really, really powerful tool at your disposal. It can be a little bit complicated to get used to, but once you have nailed it down and figured it out, it's really, really helpful in doing in-depth analysis. So in some of the challenges in this section, you'll have a chance to get some hands-on experience with that having clause. Start with types of joins, and before we can talk about the types, we probably need to know what a join is. So in SQL, a join is a way to basically connect two or more tables so that they appear as a single set of data. It's used by combining the columns that are common in both or all of the tables, and a really good indicator that you have a column that can be joined on is a primary and a foreign key. So we talked about those in earlier sections, and we kind of went through examples of how they might be connected, and we would connect those in the form of a join. Now, typically the join keyword is used on two or more tables, but it can also be joined back to itself, so you don't actually need another table to use a join. And when you join back to yourself, this is known as a self join. So we're going to talk about a couple different types of joins today. We're going to go over inner, left, right, full outer, and self. You should know that a cross join exists. It's basically a Cartesian product. It'll multiply all the possible combinations. We're not going to dig into this, but I wanted to make sure that you knew of its existence. So this is a visual representation of the different types of joins. In the top left, you can see the inner join, and we're going to talk about that one first. So an inner join, you take two tables, and where the keys intersect, that's the data that comes back. So in our example with albums and artists, only in the case where there's both the album key, or both the artist key in the album table and the artist key in the artist table, would we get back those results. Now, if we wanted all of the, let's say, albums, including those without an artist, we could do a left join. And basically that says, bring back all the results from table 1 and bring back the results from table 1 and table 2 that are connected, but don't bring back the results from table 2 that are not connected. Kind of the inverse of that is the right join, and that says bring back everything from table 2 and all the stuff that's matched between table 1 and table 2. And if you just wanted everything, you could do a full outer join, and that basically says bring me the data that's linked together by our keys that we've chosen, and bring me the stuff from table 1, and bring me stuff from table 2. And you'll find you probably get a lot of nulls in that scenario. So we're going to walk through each of these today, and we're going to go through some really specific examples. Let's start with inner join. On the left, you can see we have the album table. It has an album key. We have 7 different albums, the album name, and the artist ID. In the artist table, you can see we have 4 records. It looks like we're missing one. We're missing number 4 if we were going in numerical order. And that has the artist ID and the artist name. So right away, you should be thinking artist ID is in both tables. That's probably a good sign that we can join them together. So we're going to write a little query that basically does an inner join and brings us back all of the albums and artists where we have both sets of information. So we do select star, we've gone through that before, from album AL, and you'll notice we've aliased album with AL because when we get to the artist ID column, you'll see we have artist ID in both tables. We want to be able to differentiate which artist ID we're talking about. And here's where the new part comes in. We're going to use an inner join, and we're going to inner join artist, which we alias as AR, on al.artistid equals ar.artistid. So this on clause is really what makes the connection between two tables. You can connect on more than one column. You could do on this, or this, but we're just going to start with a simple on. And you can see the result on the right side is the collection of the albums and artists where we have the matches on artist ID. So we have albums 1, 2, 3, 6, 7, which you'll notice means we're missing albums 4 and 5. Albums 4 and 5 have artist ID number 4, which would probably be Eminem. But if you look at artist, we don't actually have an artist with artist ID number 4 in the artist table, so those records didn't come back. You might also notice in the artist table, we have an artist ID number 5, which is S Club 7, but if you look in our result, we don't have any reference to S Club 7, and that's because they don't have an album in the albums table. So that's really both sides of the join. The left where it exists, the right where it exists, and inner join says only where both exist should I bring back the results. Now, let's say we wanted all of the albums, even if we didn't have the artist information. In that case, we would keep our query almost exactly the same as it was before, but instead of the keyword inner, we're going to use the word left join, and you'll see how that adjusted our result. If you kind of look at the middle of our result table, we now have album key 4 and 5, which have Slim Shady LP and the Marshall Mathers LP. We have the artist ID, but the second artist ID is null and the artist name is null. Now, if you remember, null basically means like unknown, unknown. We don't have any information about that, and that's because the left join takes everything from the albums table, even if it doesn't have a match to the artist. If it does have a match to the artist table, it brings back that information. So this is a really good example of a left join where we might want all of the matching information for the albums and the artists where we have the full set of data, but when we don't have the data, we still want to bring back the album name and the album key and the artist ID, as you can see in our results under 4 and 5. If you look closely, you'll see we still don't have any information about S Club 7 because they are in the right table. They would only be joined into this data set if they had a match in the left table. Now, if we wanted to change our process and said we want to know about S Club 7, we don't care so much about the Slim Shady LP and the Marshall Mathers LP, we can change that left join to a right join, and it'll basically pull the opposite information. You'll see we no longer have albums 4 and 5 because a right join keeps everything from the right table and brings back anything where the left and the right table join together. So at the very bottom, we now have our artist ID number 5, S Club 7, but we don't have the Marshall Mathers LP information and we don't have the Slim Shady LP information. So the left join and the right join really behave in the same way, just if keeping items from the first or the second table. You could also rearrange the tables in your query and keep it with a left join and you still get the same result. Now, if you want everything, you can use something called a full outer join. It might be called something different depending on your dialect of SQL, but basically that brings back all of the results that we looked at in the left join and the right join. So now you'll see we have the matching information for albums 1, 2, and 3. We still get information for albums 4 and 5, which are Slim Shady LP and Marshall Mathers LP. But because the artist ID doesn't exist in the artist table, we don't have the artist name. Album 6 and 7 come back as we might expect. And then the final artist, S Club 7, you see we have no album information, but we still have the information available about that artist. So that's kind of the spectrum of the joins that you'll use most often. Typically, I find inner joins and left joins are pretty common. Right joins, maybe a little bit less so. Full outer joins, you just want to be careful because you're really bringing back a large set of data, and it might have some unintended consequences. All right, so let's talk about self-join. So a self-join is a way that you can connect a table back to itself. In a similar manner, you can do left, inner, outer, full, but you might want to do this for some interesting situations. We're going to use a different table to demonstrate. So on the left here, you can see we have the employee table. We have 3 columns, employee ID, employee name, and manager ID, where manager ID connects to the employee ID of the manager. So let's walk through a couple examples. In the first record, employee number 1 is John Doe, and John Doe does not have a manager, so that's not super helpful. But if we look at employee number 2, Sally Smith, their manager is manager ID number 6, and we look at the very bottom of the table, manager ID number 6 is Becky Jones. So what we want to do is bring back all the information from the employee table, but also add on the manager name. So if you look at our query, what we're basically going to do is from employee, we're going to alias it as E1. We're going to left join back to employee, alias it as E2. It's key that we alias this table because all of the columns are going to be named the same. And we're going to use a left join because we still want to bring back those employees that don't have a manager. So in this example, John Doe and Becky Jones, we want them in our result set, even though we don't expect them to have a manager name. So we're going to join on E1 manager ID equals E2 employee ID. So let's walk through what that looks like. For Sally Smith, E1 manager ID is the number 6, and E2, which is basically, imagine a whole nother copy of this table, employee ID is number 6, Then for any time we reference E2, we should be talking about the manager. And you can see in our select statement, we have at the very bottom of the select E2.employee name as manager name. So self-joins can be a little bit confusing, but once you harness their power, they can be super helpful, especially in this sort of scenario where columns reference other, or columns can link to other columns in the table. So let's take a look at the result of this query. On the left, we have our result set. We have employee ID number 1, employee name John Doe, no manager ID, and no manager name. And that's exactly what we'd expect. In our employee table, John Doe doesn't have a manager, and we did a left join, so we still want John Doe's information to come back, knowing that the information from the right table won't exist. Now, let's take a look at Sally Smith, employee number 2. Sally Smith has a manager ID of number 6, and we would expect manager name to be Becky Jones, and perfect, Becky Jones is the manager name. So you can see for Mike Jones, Karen Smith, and Sean Doe, all of that information came back as well. And then finally, if we look at Becky Jones, they have no manager and they have no manager name, and that's exactly what we'd expect because we did the left join. So let's begin with case statements. So oftentimes when you're writing a SQL query, you want to calculate either some business logic or perform some sort of if-then logic, and a case statement is a great way to do this. So take a look at the table we have on the left. Artist shows has artist ID, an artist name, and a count of shows performed. Now, if we wanted to bring back the results, like maybe say an artist name, and if they were famous or not from this table, we could use a case statement. We need to determine the logic, is like what makes them famous. And let's say if they have performed less than 100 shows, they are not famous, and they've returned 100 or more, and they are famous. So on the right, you can see the result, and basically we bring back the name and then the words true or false. But let's dig into the statement that got us there. So as part of the select statement, we have case when, and then we have some sort of operator that results in either a true or false statement. If it's true, we put then and then the true scenario. Else, we can put what happens when our statement is false. So if shows is less than 100, then the value becomes the word false. Otherwise, the value becomes the word true. And then we need to end it with the keyword end, and we can alias it as famous. So this is a great way to kind of perform some if else statement. You can have multiple. So you could say when shows less than 100 and greater than 10, then kind of famous. You could have multiple when statements. You can have only one else statement though. So you can have multiple when statements for different scenarios, and the else will basically be the catch-all. And then you always need to start with case when and end with the word end. And then it's typically best practice to alias it as some sort of a column name. So let's kind of jump to a different portion of the SQL query, and that's like and wildcards. So sometimes we don't know the exact value, or maybe we know a handful of values that we want that have a portion of their string in common. We can use the command like, and we can use the percentage sign as a wildcard. And that will basically allow us to say, bring us back anything that matches this in some particular way. So if you have a wildcard before the B and after the B, like in our example here, then anywhere that a capital B appears, it will come back. If we had the wildcard just after the B, so if we didn't have the percentage sign in front of the B, we just had it after, it would show us only artist names that started with B. And on the flip side, if we had the wildcard in front of the B but not after, it would show us only artists that had a capital B as the last character. And you can see in this example, we have select artist name as name from artist, where artist name like, and the like is the key word. You can't just do equals when you're using a wildcard. You have to use like, and then you can use the wildcard either before or after, and the percentage sign means unlimited characters. You can get some more specific if you have a certain number of characters. There's a lot of in-depth work you can do with like and wildcards, but for the purpose of this scenario, the percentage sign basically means anything can be before and anything can be after, because we've used percentage before and after. and it'll bring back results that have a capital B somewhere in the artist name. You can see on the right side, our result is Britney Spears because Britney starts with the B, and Backstreet Boys starts with the B, but also contains the B in boys elsewhere in the name. So let's talk about limits and offsets. We already talked about ordering, and you can use a limit without an order. Typically wouldn't make sense, but let's say you have a query and you only want a specific portion of the results. So oftentimes this is a good way to get the top or the bottom result on a specific column. So in our example, we have artist name. Now we have salary. We have their ID. We're going to bring back the name from artist. We're going to order it by annual salary descending. So that's greatest first. And then we're going to limit 1. So we've already covered the order by, and basically what that will do is take our result set and sort it with the greatest salary first. And then if we limit to 1, it will only show us the first result, which in this case basically shows us the artist name with the highest annual salary. Now, you can limit 2, you can limit 3, you can limit 1. Typically, you'll see limit 1 as a common example, but you can also use offset. Now, I'm not sure if this applies to all SQL languages, but a number of them have this concept of an offset, which is instead of just bringing back the top one, we can bring back one that is offset from the result by 1. So basically, in this scenario, we're saying, give me one record that is 1 space from the top. So that would be 2. So this would be the second most highly paid artist, which in this case would be Backstreet Boys. So offset's not used quite as often, but it's definitely important to know in case you see it in a query somewhere, or if you have a really specific example and you want the second highest paid or the second most of something, offset's a great way to accomplish that. Now, we've already talked about where, but I want to call out a couple things. In our previous sections, we did where something equals something. And in fact, you can do greater than, less than, greater than and equal to, less than or equal to, or not equal to. So in this example, we want to know all of the artists where their salary is greater than or equal to $800,000 and their artist name is not S Club 7. So in order for results to come back with this and, it has to be true for both of these scenarios. So their artist annual salary must be greater than or equal to $800,000, and their name cannot be S Club 7. So if you look at the results on the right, we see Britney and Backstreet Boys come back. And let's take a look at our salary table and just kind of walk through this process. So Britney Spears, her salary is greater than $800,000. That's correct. And her artist name is not S Club 7. Perfect. Backstreet Boys, same thing. They are $5 million, so they make more than $800,000, and their artist name is not S Club 7. LFO, their salary is not greater than $800,000, so they don't come back. We don't even make it to the second portion of the where clause. And finally, S Club 7, while their salary is greater than $800,000, the artist name is equal to S Club 7, which would result in a false, and therefore their results don't come back. So it's important to really think about two things: the way that you're going to be filtering either greater than or equal to, less than or equal to, or not equal to, and your ability to basically pile on the logic and make your filter even more constrained by using an and. Instead of and, you could also use an or, and in this scenario, if either one of these situations becomes true, the results will come back. So if the annual salary is greater than or equal to $800,000 or the artist name is LFO, let's bring them back. Now you can see we have Britney, Backstreet Boys, and LFO. Even though LFO's salary is not greater than $800,000, because of the or, we are bringing back the artist name LFO. And finally, let's talk about between. So in addition to greater than, less than, you could do where annual salary greater than this and annual salary less than this, but you can just use the between. So this works really well with numeric and date values. And you can basically say, bring me back all the results where annual salary falls between these two numbers. So the format is where column between lower bound and upper bound. And this basically says, show me everything that's between 2 million and 100 million, or 2 million and 10 million, I'm sorry, 2 million and 10 million. And that should bring back the Backstreet Boys because they are the only salary within that range. Now let's cover some other additional SQL commands. This first table talks a lot, or this first example talks more about ways that you can manipulate tables. So you can create a table. Basically, if you have a new table, you can create it with or without data. You would want to name the table, name the columns, and give them types. So you can see in our example, create table hashtag physicians with columns physician ID, which is a varchar 50, and physician name, which is varchar 100. If you want to delete a table, you can use the command drop table, and drop table hashtag physicians will basically delete it and all of its data. You can update records within a table, and you can do that in a number of ways. But for this example, we're going to update physicians table. You want to use set, then you say the column name and equal to the value. So we're going to set specialty equal to cardiology. We could do that for everything that would make all physicians cardiologists, but we want to filter it where physician ID is 1, 2, 3, 4, 5. So the result of that command will basically be in our physicians table, any record where physician ID is 1, 2, 3, 4, 5, their specialty will now become cardiology. So update works on a portion of the data, or it could work on all of it. Delete also can work on a portion of the data, and we might want to delete all the physicians where their specialty is cardiology. So delete from physicians where specialty equals cardiology would delete those records. The table itself will still exist. It's not like drop. It'll just remove those records from the table. If we want to delete everything from the table, but not delete the table itself, we could use truncate table in the table name. And basically that says, keep the table structure, but delete all of the data inside of it. Now, a command that you probably will see is insert. And basically what you can do is once you've created a table, you can take some data either by hard coding it or selecting it in a query and insert it into that table. So typically you need to choose the table name and the column names that you're going to insert, and then the select statement. So in this case, we want insert into physicians, the column physician ID, the column physician name, and we're going to select two values, 1, 2, 3, 4, 5 as a physician ID, and Dr. John Smith as a physician name. So once we have ran that, basically whatever was already in that physicians table will exist, but now we'll have a new record with ID 1, 2, 3, 4, 5, and physician name, Dr. John Smith. Now let's talk about some commands that you can use in your queries. And as you have it, we're going to start with in or not in. So instead of just equals or not equals, you can use in or not in if you have a list of values that you want to evaluate against. So in our example, we can see we want to select star from cases where diagnosis code is not in 97.1 or 060.8. And what that will do is bring us back all of the results except for those where the diagnosis code is either 97.1 or 060.8. Now you might think in this example, why don't I just use an or? And you totally could. But what happens when your list is 27 things long? Or even more importantly, if your list is another select statement from a different table. You can do the flip side. If you want it only where it is in, you would only get records back where diagnosis code is 97.1 or 060.8. Some special formatting for dates. If you have a date column, you can use day, month, or year on the front of it, and that'll basically just give you back that portion. So in this example, we have year wrapped around our date column of 2012, January 1st, and the result will just be the year 2012. We already talked about like. This is just another reminder that you can use like with wildcards. Substring is an interesting command. If you have basically some sort of a value that you want just a portion of it, you can use substring. The format might vary based on your dialect, but typically what you'll see is use the command substring, the value, or what's more likely the column name, and then the start index and the end index. So in this case, we want to start with the first character and end with the fourth, and that will basically give us CARD. We could do the same thing with left, which will just give us the left 4 characters. We could do the same thing with write. That would give us the right 4 characters, which would be LOGY. But substring is really interesting because you can wrap it with other items like char index, or you can strip something out of the middle, and you can get some really complex logic going. So let's talk about what char index is. Basically, what char index does is you first pass in the character you're looking for, and then you pass in the value that you want to search. Now, typically that would be a column name. So if we did select char index period, comma, maybe a column name diagnosis code, when the column name or the column value is 97.1, it'll send us back a 3, which is the index of the period. And now you can see how we can start to use that with substring to say, we want to take all of the data after the first period. Instead of hard coding the 1, we could say use char index period, then our column name, and then that will basically take the 3rd to the 4th characters in our substring. If we want to just replace some text straight up in our columns, we can use the word replace, and we'll put in first the column name, the value that we want to replace, and then the value we want to replace it with. So in this example, we want to take the card out of cardiology and make it into rad for radiology. And this command would basically result in the word radiology coming back. Now, we talked about limit as a way to only get back a portion of results. Many different dialects either have top or first as a command that you can use, but you use this in the select statement. So if we use select top 10 star from cases, it would basically show us the first 10 rows from the cases table. Ordered or not, it doesn't care, but it is a helpful thing, especially when you're just trying to dig into your data a little bit and understand it before writing a full query.